Okay, can you hear me?
Yes, I actually have a question. Could you explain further what you were talking about to me in the tutorial because I couldn't completely get it?
Okay, sure. So yeah, that's an important point that I was planning to go over anyway today. So let's do that. So I wanted to have a discussion on the Dirac function, and that's what you were working on in the tutorial yesterday. So let's just write that. So the delta function, the identities that you proved in the tutorial, all the identities, they only hold under the integral sign, okay? So for example, one of the identities that I asked you to prove was that suppose you have some well-defined function and you're taking its derivative and you multiply that function with a delta function, and then that is equal to minus the function times the derivative of the delta function, like so. So what we mean when we write equations like this involving the delta function is that both sides, let me just use a shorthand notation where this is f prime and this is delta x minus x prime is equal to minus f delta prime x minus x prime. We put an x here because that's important. So what we mean when we write equations like this is that there is an integral sign with the appropriate limits on both sides, okay? Yeah, so this is what it means. So what Saif was saying is that, yesterday he argued that if this is the case in general, it does not mean that the integrands are equal to each other, right? So if you have, for example, some function g of x, and you integrate it, and it's equal to minus another function, say h of x, d of x, and your limits are minus infinity to plus infinity, this does not imply in general that g of x is equal to h of x, right? This is not true. So, and a simple example of this was provided by Dian, is suppose that I take both to one side, then on the left-hand side, I have g of x plus h of x and d of x, and this is equals to 0. Now, there are non-trivial functions, such as, say, let this function be psi of x, for example, odd functions for which this is 0, but the function itself is not 0, right? So, for example, odd functions satisfy this, right? And therefore, this being 0 does not mean that this integrand is 0. And therefore, this equivalence is strictly only true under the integral sign, okay? Now, because we are dealing with delta functions, we have more information than just this equation, right? We have more information. So for example, we have some intuition about the delta function. So for example, we can say, okay, the delta function is a function which is the, say, limit of the Gaussian, right? So you saw that if you take a Gaussian and this is epsilon, and this is, say, 1 over epsilon, then, if you, or 2 epsilon, whatever, I don't care, the exact normalization, but it could be, the area is something, so, up to some order 1 constant, so that under the curve remains 1 in the limit where the epsilon goes to 0, right? So we saw that that was a representation of the delta function. And, if you take the derivative of this guy, what do we get? here, the derivative is positive. Here, the derivative is 0. And here, the derivative is negative. So this should be on the positive side, not x. So that, we have, if I take the derivative, it'll roughly look like something like this, right? So, we see that, in the epsilon goes to 0 limit, this probably is going to give me a minus of the Heaviside theta function, right? Up to some sign. So, and so if I multiply this function by another function in that limit, when we multiply this by the same function, we see that, this function will sample its value here and subtract it from the value here. So roughly speaking, in the limit where epsilon goes to 0, in the, the left-hand side is taking the derivative. So in that sense, we can say, okay, this is true, quote unquote, without the integral. But at the end of the day, that's actually not completely true because, we are dealing with singular quantities, right? As singular quantities, these are just singular quantities. So we don't want to, just one second, okay? My air conditioning is misbehaving. Oh, I see. Okay, yeah. All right, cool. So, Saif, does that answer your question?
Sir, what do you exactly mean by singular quantity?
Yeah. So basically, when epsilon goes to 0, what happens is that this Gaussian becomes a singular Gaussian, right? The height of the center point goes to infinity, right?
Oh, I see.
Because,
yeah.
Yeah, and the width goes to 0. So it's basically at that limit, it's an infinitely high and infinitely thin spike, but in a way such that the area under the, inside the spike is 1. Right? Because another property of the delta function is that, delta of x, d of x is it's just 1, right? Because here the function that we're looking for, f of x, is just the identity function, right? And here then we are just looking at f of 0, which is 1. Okay?
Yeah, makes sense.
Okay. Any other questions? I mean, I have more to say about yesterday's tutorial, but yeah.
I have a question about the last question যে একটা আইডেন্টিটি ইউজ করে দেখা যাচ্ছে যে এফ অফ এক্স হচ্ছে যেখানে ডেল্টা অফ এফ অফ এক্স হচ্ছে একটা হয় ওখানে আমরা যে টেইলর এক্সপানশন করি তখন তো একটা জিরোর লাইক একটা জিরো চুজ করি তখন ওইটার আশেপাশে ওইটার ভিসিনিটিতে হচ্ছে ইয়ে করা যায় তো ইয়েতে ওই ফর্মে হচ্ছে নিচে একটা নিচে না একটা সাম আকারে
একটা সাম আছে, হ্যাঁ, right. How did the sum come about? That's your question, right? Yeah. Okay. So yeah, let's do that. So so I'm planning to actually prove that identity.
আমি হচ্ছে যে আমি আচ্ছা স্যার sorry.
I think I'll come to that, and maybe you can comment on that when I come to that. Okay.
Okay, sir.
Yeah, is that all right?
All right, sir.
Okay. So I mean, I'm trying out new headphones, so please let me know if there's issues with the with the sound, because yeah, I'm trying out new Bluetooth headphones. Okay, so before we prove the last identity in the tutorial, I wanted to just go over the one before that, which was if the argument of the delta function is a times the integral variable, then that is equal to the delta function divided by the modulus of that a. Here, a is a real number. It's a real constant, okay? So to show this, we integrate left-hand side from minus infinity to plus infinity. This is pretty easy to show. And then what we do is that we just divide and multiply by a. So we have delta of a of x, and here we have 1 over a, and then here d of ax. Now, a can be positive or negative. So yeah, a is not 0, okay? A can be positive or negative. Now, if I now redefine my variable ax to be y, then if a is positive, then you see that these limits don't change. If it's a positive real number, which is finite, then these limits don't change. But if a is negative, then we see that these limits will flip, right? If these limits flip, then we can change the limits again, but we have to compensate that by a minus sign. Is that clear?
Yes, sir.
Okay. So we can write this as an integral from minus infinity to plus infinity, delta as a function of y, d of y. So I'm defining y to be a of x. And then we have 1 over a, and then I have to say it has to be multiplied by the sign of a, right? Is it clear why including the sign of a, encapsulates both situations where a is positive and a is negative? Because when a is positive, the limits don't change. And when a is negative, that sign can be absorbed here and the limits will change, right?
Sir, I have a question here.
Yeah.
The delta function is symmetric on the both side of the x-axis. So will the change of limit, I mean plus infinity in the position of minus infinity, will it change the result?
No, it doesn't. Yeah.
Okay.
Yeah. So, okay, so what is this thing? This is nothing but 1 over modulus of a, right? And then y is just a dummy variable. I can rewrite as this integral in terms of x, right? So now if I compare the left-hand side, which is this thing, and the right-hand side, we see that delta of a of x is equal to delta of x divided by the modulus of a. Okay, so this is a nice little identity that is actually very important. The next identity is even more important, but the next identity is dependent on identity. Okay, so suppose, and in physics this happens quite often, you have a delta function which is a function of a function, which is whose argument is a function, but you have to integrate it with respect to, say, x. Okay, this is a very important case. What do you do then? Now we assume that f of x is some normal function, and that f of x has zeros at, say, xi's. Okay, I is some index. So I can go from, say, 1 to ... and over there. Okay? Then, how do we evaluate, say, minus infinity plus infinity, delta of f of x del dx? How do we evaluate that? Well, notice that delta of or just say delta is non-zero. So only when its argument is 0. Right? So it's only when f of x is 0, that's when this thing is non-zero. But we don't know exactly how f of x behaves as we change x, right? There could be because we're integrating on the real line, there could be more than one point at which, the function f of x goes to 0. And so we have to include all those in our computation. So what we can say is that, okay, so we say that, okay, let's just take this guy. Okay, and we can write this as sum over, we just want to integrate them around the zeros, right? Minus epsilon, where epsilon is a small real number, a positive number. And this is the trick. So we are just assuming that in that little interval, at twice epsilon, there are no zeros of f. Okay. Do you agree with this, Nian?
Yes, sir.
Yeah. So, and then what we can say is that, okay, near the x equals to xi, we can say f of x minus xi is f at xi plus x minus xi d of f by d of x by dx evaluated at x equals to xi, right? But xi is a 0, and therefore the first term is 0, right? This guy vanishes by definition. So we have left over x minus xi d of f d of x equals to xi. So let's put that in parentheses so that this thing becomes equal to sum over I. And now we have an integral, and now delta. And inside, the integral, we have x minus xi d of f d of x at xi's, okay? And here we have x I minus epsilon to xi plus epsilon. And then we can say that, okay, now I can use, this identity, because this identity, you might argue that, well, we have to integrate it from minus infinity to plus infinity on both sides. But I'm just going to say no. I mean, we actually have to just integrate around a small region around the point x equals to 0, right? Because the delta function doesn't care about what happens away from those points. And we can use this logic here because, we are just integrating in the neighborhood of the 0. So we can write that as, the limits remain unchanged, but here x minus xi divided by this constant, its modulus value, x equals to xi, d of x. But now see that, we have converted the integral in such a way that the argument of the delta function goes to 0 only at one point for a given point of time. Just 1 second, okay? Just 1 second. হ্যাঁ আচ্ছা ঠিক আছে ওকে আমি ক্লাসে আছি কিন্তু আমার ফোন আসলে আমি রিসিভ করব আমার বাসায় টাকা রেখে আসছি ওকে ঠিক আছে ওকে বাই I'm sorry about that. So, can you hear me?
Yes, sir.
Okay, good. So now, because we have now converted the integral into variables, where the argument only goes to 0 at one point for given I. We could have done it in the previous, we can now change the integral limits to -infinity to +infinity. And then, we assume that, the sum and the integral, commutes, which is a kind of a dodgy step. And that's why, you have to essentially invoke some theory of distributions, which I'm not going to do. And therefore we arrive at the wonderful identity that the delta function of a function is equal to sum over all the zeros of the delta function divided by the derivative, the kind of the Jacobian, if you like, a derivative of the function evaluated at the zeros, okay? So this is an extremely important identity. Like, I cannot emphasize how important this is. Like, people had forgotten, like, our physicists have been very cavalier about this identity in such a way that when the first, a lot of papers in the early 50s, 60s, I think, in quantum field theory arrived at wrong results because they forgot to take into account this determinant. And well, in quantum field theory, this becomes a very famous determinant called the Fadaev-Popov. I would also say Feynman determinant, and it has important physical consequences. Okay, I think any question from this?
কোয়েশ্চেন না, বাট মানে স্যার আমি হচ্ছে মানে গতকাল এটা নিয়ে ভাবতেছিলাম মানে এটা কিভাবে করা যায়। তখন হচ্ছে মানে আমি হচ্ছে মানে বারবার সাম আসতেছিল না মানে, কিন্তু পরে চিন্তা করছিলাম যে মানে এফ অফ এক্স এর যে পয়েন্ট গুলোতে 0 হয় ওই পয়েন্ট গুলো বাদেও যদি আমরা মানে প্রত্যেকবার এক একটা 0-র আশেপাশেও করি, কিন্তু পরে যদি যোগও করি মানে এক্স এর ভ্যালু ইনপুট করলে ওটা যদি যে কোনো একটা 0-র আশেপাশে হয়, বাকি সবগুলো টার্ম তো ওই ভ্যালুর জন্য 0 হয়ে যাবে। সো আলটিমেটলি মানে এই মানে আর মানে এই ইয়েটা কি মানে এভাবে কি করা যায় কিনা মানে এটা?
Right. I mean, I mean, I think I understand confusion, but the way I see it is like this. So you have, you're doing an integral, and this is the line you're integrating over x. But since that is actually not your argument is some function of x. As you're moving it in the x direction, what is happening in your integral is that your integral is moving, it's the argument is moving along the real line, but not in a monotonic fashion, right? It can move up, it can move down. So every time, so suppose that, right. So, and every time, so this is the f, and this is, say, f of x, right? This is f of x. So, and as you, sweep along x, right? And f of some, say, origin here, right? As you sweep along x, what you're doing is that you're moving along f of x and get to the 0, the origin. And then you get a contribution. But then, because it's not a monotonic function, it can turn back and it's going towards a negative again. And then again, it crosses the 0. And then you get another contribution. And it can do other things, right? It can go like this stuff. But at the same time, on the integration line, variable is just going in one direction. But f of x going in it can oscillate and do stuff like that, right? So I don't know if that helps. visualize it.
আমি হচ্ছে মানে এক্স আর ওয়াই অ্যাক্সিস একে মানে যে কোনো একটা র্যান্ডম সাই অফ এক্স
Function name,
যেটা
right?
যেটা হচ্ছে এক্স অ্যাক্সিসে হচ্ছে জিরোতে লাইক ইন্টারসেক্ট করতেছে, তো ওই পয়েন্ট গুলোতে হচ্ছে ডেল্টা সাই এফ অফ এক্স হচ্ছে
Exactly.
স্পাইক থাকবে এভাবে।
Exactly. Yeah. I think you got it. So yeah.